The other thing I'd like to pass out is from a work of fiction, but don't be bothered by that, because as soon as I read it, I realized that whoever wrote that chapter must have had an analysis, or he wouldn't have known how it sounds, how it goes when it's not Ingrid Bergman in the movies. It has the valid flavor of a real psychoanalytic hour, but of course I had to get permission. The author, Millen Brand, a book that was quite widely known, I think maybe it even got a prize, The Outward Room, published in 1937. In writing back, giving me permission to reproduce it, answered my question. I said, you must have been analyzed or you wouldn't know how to write this particular chapter. And he said it had an analysis, and even though the protagonist of the heroine is a girl, he was actually the person who's in the book, in the novel. This was a session that he found quite fascinating, and since he knew he was going to write about his analysis as part of this novel, he wrote down this stuff right after the session. So it's not a verbatim protocol, but it's such a nice example. So even though it's from a work of fiction, I think it's worthwhile showing it to you. Two final points about psychoanalytic inference that I want to make, and then go back to talking about theory testing in general. You may be a little surprised that on the subject of psychoanalysis, I elected simply to spend a session on the psychoanalytic session rather than on the experiments or on the correlational data or on some aspects of primate ethology that bear on Freud, for instance, and the work of the developmental psychologists. And the reason for that is my belief that the strongest basis for a rational person to think there's something to Freud's ideas about the unconscious is the psychoanalytic hour itself. And if that is a haywire way of studying the mind of an individual, then I do not believe that any of the other ways, like correlating anality on the multiphasic with the Rorschach, are going to be persuasive to people, or rationally should be. Now, I'm not committing the fallacy of saying that only the first context in which somebody notices something could ever be the strongest evidence. That would be dumb. In the case of psychoanalysis, that's my view. And if the free association method, the imposition of the fundamental rule, and the analyst listening and thinking he discerns themes and then making predictions and seeing whether they pan out, if that whole process is what Fliess said it was at Achensee, just reading your mind into the mind of the patient, if the difficulties, the statistical difficulties of saying how well does this converge that I raised last time with analogies to history and fossils and courts of law, if those difficulties are insuperable, so that we end up saying this is a kind of a cute gimmick he had with the couch and all, but it's not a good way to collect data and to test theories about the mind, then my view is that psychoanalysis is in very, very poor shape. And one cannot profitably talk about the metapsychology in a course like this. You'd have to spend a long time on that. The core problem of psychoanalysis, as I view it, and a lot of people don't agree with me about this, the core problem of psychoanalysis is the psychoanalytic session. That's where Freud hit upon his notions. And if that's a crummy way to collect data, or the interpretation is very largely arbitrary, capricious, projection by the analyst rather than seeing the relationships that are, quote, really there under the surface, then I think that psychoanalysis is in very poor shape, despite the efforts of experimental and personality psychologists to study it by other methods, which I'm sure you're aware by and large have been a very mixed bag of results. I mean, I doubt anybody reading Sears' classic work. Sears just died last week, I noticed, age 80. I doubt any psychologist gets converted to or away from some belief in psychoanalysis by reading those studies, or by reading Silverman, or by reading any of the other experimental studies. What you get is a mix in which you can explain away the plus results without buying Freud, or if you're a Freudian, you can explain away the failures and by various legitimate moves about auxiliaries and so on that we discussed last quarter. And so that big mess of stuff is simply not convincing to people on either side of the street. So that's why I think that the psychoanalytic session itself is the place to concentrate. You might ask if I was that interested in psychoanalysis as a young man, why I never published any research in the subject. Well, I did some in the early 50s, and McCorkadale and I decided that we had wasted a lot of taxpayer money, that we didn't know how to study the psychoanalytic hour. That's what we concluded. And there is a very recent study from a California crew whose name I have now forgotten. Does anybody know the group at Mount Sinai? Well, I'm sorry, I can't remember the reference. A whole book. They did it right by my lights, insofar as you can study this damn stuff scientifically at all, which I sometimes doubt, but insofar as you can, they did it right. And they're quite pleased with statistically significant correlations of 32 and so forth, which I tend not to be. The other general remark I'd like to make for the benefit of those of you who are clinicians and counselors, it is imperative to distinguish, especially at Minnesota, between two cases of doubt about clinical evidence or clinical experience. And some of my brethren in hard-nosed psychology don't make this distinction, although I keep trying to educate them. There's a very important distinction between saying there is no convincing quantitative or experimental evidence for this theory, so I'm going to have to fall back on my clinical experience until such becomes available. There's a difference between that statement and the statement that quantitative and experimental evidence tends to be against this theory, but I'm going to believe my experience anyway. The first is rational, the second is usually irrational. It's perfectly all right for a clinician or a counselor who is daily forced to act on his beliefs or her beliefs, when to interpret, when to shut up and stuff like that, what kind of diagnosis to make, to rely on clinical experience, your own and your elders, your supervisors, your role models, when there isn't any adequate quantitative data. That's perfectly rational. We do that every day of our lives, and I have harped on that a lot in this class. What is not rational is that when a clinician believes in the draw person test or the Minnesota tennis ball projected bushel basket test, devoutly believes in it, and there are 25 studies and they all show it's horseshit, and he goes and believes it anyway. He continues to tell a judge that the patient is dangerous and make clinical decisions in the face of a massive quantitative support that shows the instrument is not valid. That's what's a mistake. Not just a scientific, scholarly mistake, but a moral blooper. I mean, you're taking the taxpayer's dollar and you're dealing with a human being's life and health and misery on some crummy instrument that doesn't work. That's scandalous. So that's the distinction one should always make. When it's hard to study a thing in a scientific, quantitative way without doing it simple-mindedly, then you may have to rely on poorer evidence as a decision maker. And if you say, well, no, the way I was trained, especially in Minnesota, I can't tolerate that, then the answer is you can't be a clinician, brother. You better go do something else. Be a rat psychologist or a psychometrician or something. But if you tell me I want to be a clinician, but I'm not going to make any judgments when to intervene, what to say, what to predict, whether to take the patient in therapy, whether to advise group, whether to see him inpatient or outpatient, I'm not going to be able to do any of these things unless I have strong scientific proof, strongly replicated. You got to get the heck out of clinical psychology and earn an honest living telling shoes or doing mathematics or something, because it can't be done any more than the doctor or the lawyer or the certified public accountant can function if the standards of evidence are as high as we require in a seminar. That's the nature of the case. I mean, the mind is a mess. The mind is complicated and the psychology is a mess. So if you're out there making decisions about people and collecting money besides for doing it, if that goes against your scholarly conscience, then you should go and do something else, right? What I do not approve of is people who withstand large masses of evidence done in different labs, not simplistically designed, which show that a certain procedure doesn't help people or that a certain test is not valid, and continue to do it anyway. And there's all sorts of people with PhDs out there in the boondocks that are doing that at your expense if you're a taxpayer. Okay, so much for psychoanalysis. Now I want to spend some time on going back to this problem of assessing the status of a scientific theory. How do we do that if we have come to realize that the standard traditional use of significance tests refuting H null is not a very powerful way to do it? I do not say it's absolutely worthless, especially at an exploratory stage, but the widely held view that you get really strong support for theories because alpha is only 0.5, I hope between Licken and me we've convinced you that that is a delusion, even though it is the received method of going about things in soft psychology. I guess I have distinguished, but I'll do it again, between the weak use of significance tests and the strong use. The weak use is the conventional one. It's the use that occupies practically every article in the Journal of Personality and Social Psychology, for instance, in which the theory is so weak that it's not capable of saying anything more than that the boys should be taller than the girls, or the whatever, that the schizophrenics should be shyer than the manic depressives, and so on. The illusion that you have subjected the theory to a big risk, so that if you've ever heard of Popper, you say, well, I did that. I'm holding out for 0.01 instead of only 0.05. And that comes, the reason that that's an illusion, even though it is a statistician's risk, is that substantively, due to the crud factor, and due to the usually large set of alternative theories, each of which is capable of saying the boys will be taller than the girls, or the girls will have bigger vocabulary than the boys, or the upper class fewer cavities in their teeth than the proletariat, etc., etc. Because of that crud factor, and because of the multitude of quite plausible alternative interpretations of a mere difference in favor of one group, that does not mean a big epistemological risk, even though it does mean a big risk in the sense of the statistician. It's as big as you make alpha small. The strong use is the use that goes backward from this one and is not available to us unless we can strengthify our theory a little bit more. In the strong use, the theory specifies a point value or an interval, and the significance test is used backward from the first way. Namely, it asks, did we hit or did we miss? Did our empirical results come off from what the theory said they should be? And as I pointed out before, the original use of chi-square, as Carl Pearson invented it, was of type 2, the strong use, where the theory specifies some distribution shape, and then I compare the observed frequencies in the cells with the theoretical frequencies, and if I get a significant chi-square, my theory has been falsified. When the theory is so weak that you can't do that, that it doesn't predict how many there should be in this cell or what the mean value should be, then in the cell case, like a fourfold table, what did the psychologists do, taking it over from the statistician? They said, well, we can't predict how many cases are in each of these cells, but we'll say if the theory has nothing to it, then maybe these things shouldn't be related at all. And if these things are not related at all, then the way you predict how many tallies there are in a cell is by taking the product of the marginals, making use of elementary theory and probability. And in that case, you are comparing the observed results with results from predicted from a theory that says it's all chance in this table. So the use of a significance test, even though the math is identical, I mean, it's the same formula for chi-square with the gamma functions and so many degrees of freedom, but the difference is fundamentally very different epistemologically. In the one case, in the strong use, statistical significance indicates departure from what the theory said should happen, and in the weak use, it says departure from what would happen absent any theory or crud factor, namely that everything is chance. Well, naturally, if you're a Popperian, neo-Popperian, you kind of like the strong use. But the strong use, as I tried to indicate at the end of last quarter, is too strong because we are now refuting a set of statements which we didn't take seriously anyway, namely that the theory itself is literally true as stated, and that the auxiliaries are all literally true as stated, and that the ceteris paribus clause is true. And that we know in psychology the chances of any of those things being literally true is not zero but negligibly small. So what we're doing here is two rather pointless exercises, even though this one, it looks more Popperian, and I guess I feel better about it, but it's two rather pointless exercises. Here we're proving that things are not totally unrelated, and we already know that, apart from our theory. And then here we're proving that they're not related precisely as the theory and the auxiliary specify, and we know that that's false too. Mm-hmm.
I think you talked a little bit about this before, but how do you feel about, say, same path analysis, where you have 2 or 3 competing path models, and you're testing them against each other? Where would this fall?
Where would you think they fall, comparing two diagrams? Not in the goofy way that I talked about the time before last, but to some traditional goodness of fit measure.
I don't think it's still in the strong category. You're still using between them.
It's hard to classify that one, isn't it?
But one advantage, I guess, I would see as well is that even though you're testing different substantive theories, if you can translate them well into the path models, they're sharing the same auxiliary substance.
Yep.
So they wouldn't differ.
Yep. If you are not allowing yourself to be seduced by some kind of a search procedure, a program that suffers from creeping induction, so I just keep sticking in more and more arrows. But you have in mind a case where you have 2 substantive theories like my son's IQ business, and which are quite different, and which lead you to draw quite different diagrams, and which therefore will give you different path weights. If you ask it in terms of is one better than the other, it looks like type 1. If you test each one against the data, I really don't know how to answer that question. That's a very interesting question to think about. And in any case, a much more respectable thing to be doing if you aren't doing creeping induction. Would you agree? That is, whether we put that under 1 or 2 category, that is a more respectable thing to do. Popper, of course, always prefers the ideal case, pitting 2 theories against one another. He says that, sure, sometimes it's a theory against the fact. Historically, the most interesting experiments in the physical sciences have been pitting theory 1 against theory 2. That's a good question, and I'll have if one and says, what have we got instead? What is the question we would like to be answering here? This answers the uninteresting question, are the relationships literally zero? This answers an almost equally uninteresting question of whether the relationships are precisely as the theory says they ought to be. What would we like to be doing? Well, what we would like to be doing, if we could get some kind of a probability number, would be some expression of, to the extent to which it's a Salmonian damn strange coincidence, and it may be that that's going to be very hard to quantify. I kind of like to use a word, I don't know if it's in Webster, but I'll make it up if it's not. You get to be an old codger like me, why you sometimes feel free to make up terms, as long as you don't think you're solving scientific problems that way. And the word that I need here is numerify, because measure has very strong connotations to some people, particularly psychometricians. They want to know about interval scales and ratio scales, and thank you. And quantify isn't quite as bad as measure, but some people even have more of a loading on that. And numerify is the feeblest word I can think of here, and what I'm going to talk about is pretty damn feeble. Numerify means attaching numbers to observations or attaching numbers to facts which are at least a little more than football numbers. That is, they're a little more than nominal use. The fullback is number 37. They're a little more than that. They're not even quite rankings because they can be probabilistic or quasi-rankings. They don't even say for sure that A is better than B or B is better than C, but they say A tends to be better or something like that, or something about a probability. And we'd like to numerify the extent to which we find something that's a damn strange coincidence. Now, that corresponds to numerifying the Popperian risk as generalized. The trouble with the Popperian risk is that it's the risk that you may miss. And Popper, as I pointed out winter quarter, when Popper moved from truth to verisimilitude, he never managed to do some corresponding move in the concept of risk. He was pleased with modus tollens. It's a nice, clean logician's concept. And when we begin to allow a theory to have some brownie points because it does rather well, even though, strictly speaking, it misses, we aren't quite talking about Popperian risk anymore. And the only way I know of to generalize the concept of Popperian risk to the case where a theory does rather well but it misses, strictly speaking, is to switch to a Salmonian coincidence. In other words, epistemologically, as far as I'm concerned, epistemologically, a Popperian risk and a Salmonian damn strange coincidence are the same kind of animal. But the Salmonian coincidence can include near misses or almost hits. Now, if that doesn't have intuitive appeal, it's maybe because I have brainwashed you too much a la Popper. Suppose, for example, I have a feeble theory that just says the experimentals should do better than the controls. So any of this is allowed. I'm plotting now, say, a mean difference. Any value in here is allowed. Let's not talk about significance tests now. A billion cases, all right, or the value of the parameter. And what's forbidden is this. And the experimental result is this. Well, that's a little bit of corroboration. Popper wouldn't deny that. It's pretty weak. I got an even chance of being on the right side of zero. And I know that if the power is sufficient, I will get a significant deviation. So I've got an even chance, remember my model of picking theories out of one bucket and facts out of the other bucket. That's a corroboration, but weak. You wouldn't jump up and down for joy unless you'd been totally brainwashed by conventional significance testing to say that, boy, is that ever great evidence for Fisby's theory of the mind. It's rather feeble evidence. It is evidence. You could miss. Really. Take, however, the case in which the theory predicts a very small interval. Like I have some genetic theory about IQ, and I say, what do I expect to be the IQ of a biological parent and a foster parent having a certain IQ? And I have a theory that says it won't be the mid-parent IQ anymore. And now suppose my facts end up like this. Like, say, it says it ought to be 117, and it's 116. Now, I think that practically any psychologist, I know that a chemist would say, that's pretty darn good, and that impresses me a lot more than this does. But I think even most psychologists who had been hypnotized by conventional significance testing would reluctantly admit that even though this is off, it's darn close. And something that's that close, when it had narrowed down the interval that much, suggests that the theory has a sizable amount of verisimilitude, even though it is literally false, or the auxiliaries are false, or the ceteris paribus is false, or we've had an unlucky sampling error. But for it to be that close is impressive, is compatible with saying the theory has high verisimilitude, isn't it? High verisimilitude doesn't mean absolute truth. And so it's consistent with saying the theory, although literally false, has high verisimilitude. It's a strange coincidence, if the theory has nothing to it, that we'd be only one IQ point off. This is not much of a coincidence. A little bit. I said head, and I got heads rather than tails. This is a feeble coincidence. So here's a case, and Popper doesn't discuss this, except by implication. And I know why he doesn't. He had to give up the beautiful simplicity of the modus tollens, you see. He doesn't discuss this obvious point that happens over and over again in the history of physics and chemistry and astronomy and genetics, where somebody says, boy, we came darn close. This is a theory that has a lot to it. Let's work on amending it. Maybe we can fix it so it'll be exactly true, or maybe we can fiddle with the auxiliaries or the ceteris paribus clause. And we are more likely to spend time and energy working on amending this one, or oddest ad hocery of the auxiliaries, than we are to be impressed with this one, even though this one hit and this one missed. Strictly speaking, this one missed. The empirical value, the observed value, was outside the theory's permitted interval. Keep in mind Popper's remark. Scientific laws of nature are like the laws of God or the laws of the legislature. They forbid things. That's what they do. And the test of a theory is whether it forbids a bunch of stuff, narrows down what is permissible, and you get it right. So, is there some way we could concoct an index that would numerify that notion of a damn strange coincidence? And it has to contain, any index we concoct for that purpose is going to have to contain kinds, isn't it? And then it's going to have to say, how bad off are you? How far out were you? And it's going to have to put those together in joint fashion. The obvious way to do stuff like that is to multiply it. We prefer that rather than adding it. Maybe some deep reason that I haven't thought through, but that's the way we concoct such indices. And so what I've been doing lately is concocting a couple of indexes that I think would be useful to the philosopher of science in studying in studying the history of science, because of my position that I indicated to you before, that you can't solve the current, settle the controversies in philosophy of science defined as it's now being defined by anecdotes. Because case studies can only refute all or none statements, right? The anecdotal method, if you believe the anecdote, can refute a statement that says a certain event can't happen. As Bertie Russell says, one occurrence of an event shows it's possible. All right? Now, an anecdote can do that, but the anecdotes that are found in the history of science all refute general statements that nobody has ever made. And so that's not very illuminating. So that, for example, when Feyerabend tells us about Prout's law, we've talked about Prout, everything's out of hydrogen, and it's refuted by chlorine, and then now we find out about isotopes, and so Prout is back in and is revived, and is the current theory of the cosmologists about the universe. Everything is made out of hydrogen. Well, what does that case study show? It shows that the following statement is false. No theory is ever slain and subsequently resurrected. But who said that? Nobody ever said that. John Stuart Mill didn't even say that, see? So that anecdote is not very helpful to us. Or if somebody says, no theory is ever rejected on the basis of a single experimental finding, that's refuted by some of Popper's examples, his favorite being the Bohr, Kramer, Slater quantum thing in 1924, killed in 6 months. And he always lugs that one in, and then somebody else brings in one where that didn't happen that way. Well, what are they doing? They're piling up these anecdotes like a couple of clinicians, you know, Freudian, Adlerian. And the point is, the anecdotes, if taken at face value, I'm not criticizing the anecdotal method in the way the animal psychologist does now. I'm saying let's assume the anecdote is accurate. The case study is properly conducted by a good historian of science who knows how to do historiographical research. And what the episodes show, when you get somebody that's stuck to his guns, like Mendeleev and turned out to be right, or a theory that nobody believed in for 50 years like Prout and then it's revived, or the Bohr-Kramer-Slater theory that was successfully killed by one single experiment, as Popper points out. That's not disputed. Everybody agrees with him about that as an anecdote. Those individual case studies of scientific theories or individual scientists are falsifiers of general statements which, so far as I'm aware, nobody ever made, and if they did, they shouldn't have. And so that's not the way to do it. And what I push for, therefore, is saying this is intrinsically a statistical problem, inherently an actuarial or stochastic kind of problem. And if something is inherently statistical, then the best way to study it is with statistics. And so that's what I think the boys ought to do next. I have begun a paper, in the sense of I have written the outline, that's as far as I am, which I plan to write this summer, which I'll submit to a funny journal that some of you may know called Studies in History and Philosophy of Science. And it often helps for your morale, you know, to have a catchy title even before you've written the thing. And my catchy title is Cleometrics and Meta-Theory, a Modest Proposal. That'll send all the philosophers running to the dictionary to see what the heck cleometrics is, and you'll find it's not cataloged in the Library of Congress, believe it or not. Isn't that crazy? Cleometrics, the LC category doesn't include that. So what I'm going to argue in that paper is that the time has come, if meta-theory is the rational reconstruction of the empirical history of scientific theories, then not rules, principles, guidelines, friendly fatherly advice or whatever, that in general tends to pay off and that you hope that not everybody takes and that a few genius maverick general principles about ad hocing and progressive programs and falsifiability and all those principles are not rules. Feyerabend is right about that. They're not rules. They're guidelines or rough principles, and hence Hence, their performance is only statistical, and hence the proper way to study the importance of these different rules, and maybe even to find that some of them should be dropped, even as principles, see? Not just said not strict rules, but this is not even a good principle. Feyerabend says that in his book Against Method. Maximum proliferation, he says. You got a theory that isn't even in trouble, he says. We hope all sorts of smart people will think of competing theories. That's definitely not the received view of most philosophers of science. It certainly is not the received view of scientists, as you know. I mean, the usual view there is if you're doing peachy, keep solving puzzles in Kuhn's sense. Don't start making revolutions if everything is going fine. Feyerabend says that's even bad advice. We should proliferate like crazy, even when a theory is in great shape. I don't understand that there could be any way to solve that kind of a controversy without proceeding actuarially on the material. All right, so what might we do by way of an index of theory's performance, keeping in mind now that there are many properties of theories besides their ability to predict and explain facts that are important. That's one of the mistakes the positivists made, that they thought that's the only way you judge theories. Quite clear from Larry Loudon's writings that that's not the only way, that there are other things about theories, such as where they fit in with other layers of Comte's pyramid that lead us to prefer one theory to another. A theory that predicted the facts of its domain quite well and couldn't be fitted into the Comte pyramid of the sciences would not be taken seriously, even if it predicted the facts. I mean, if I had a theory about how methotrexate works in choriocarcinoma, which it does, as I remember, by fooling the cell so that when the cancer cell tries to mitose, it tries to use a substance for making the what are those strings? Yeah, spindle fibers. Yeah, thank you. It tries to use a substance for forming the spindle fibers, which are imperative to have there, that doesn't work. So when you look at the cancer cell trying to mitose after the patient's been treated with methotrexate, you get these spindle fibers all gunked up, you see. And well, now, if somebody came along with a theory that explained the facts about methotrexate on the assumption that the spindle fibers were fine silver wires, even if it predicted the facts, nobody would take it seriously, because we say, listen, it's protoplasm. It's not made out of fine wires. So there's Larry Loudon's book contains a whole chapter listing a whole bunch of characteristics that theories can have or lack that scientists use in deciding for or against their plausibility or whether they should be pursued further. I'm confining myself here to the simplest positivist empiricist thing about a theory, namely, does it predict the numbers? Well, we got to have an index with two components. And the first component is how detailed or precise the theory is in its forecasts. And I will consider there the theories, what the theory will tolerate, divided by, have I talked about the Spielraum at all? I have talked about the Spielraum. That's the range of possible values for a particular type of experiment that prior knowledge, previous research, common sense, or a larger embedding theory. It's not always the same kind of thing. It tells you what the Spielraum is. And I think that any index, whether mine is any good or not, any index that gets at Popperian risk or Salmonian coincidence has got to relate the theory's tolerance with some concept of the Spielraum. That I'm convinced about. My particular index may have bugs in it, and the reason I'm convinced about that is that if you present a person with a successful prediction or an almost successful prediction in a domain where the listener doesn't know anything about the stuff, doesn't have a clue, he never knows whether to be impressed or not, quite rightly. So if I have a theory about what controls the length of the trunks of baby elephants, and I combine, say, some knowledge of the mother's weight with some biochemical thing about mother elephants' growth hormones or something, and I say, you know, by combining the weight of mother elephants with their blood turpentine titer, I can predict the length of the newborn baby elephant's trunk within 2 centimeters. And you don't know what to do with that, do you? Unless you know the standard deviation of baby elephants' trunks, you don't know whether this is a big, impressive finding or not. I mean, suppose the standard deviation of baby elephants' trunks is 3 centimeters, then 2/3 of that is one probable error, and that means half the time that's how far off you'd be, and so you're doing as well as you could by flipping pennies. So that means your theory is not very well supported. If I tell you such and such is off by 500 miles, I've got this new instrument for estimating distances, and you say, well, what kind of distances you're estimating? I mean, if I'm off 500 miles estimating the distance of the moon, and that's 240,000, 500, is that big or little? Well, what's the current rates in astronomy? I could be off a light year. My God, how far does light travel in a year at 300,000 kilometers per second? What a huge whopping distance. Well, if I'm off only 1 light year when I'm talking about galaxies and some other sub-universe, that would be amazing accuracy for the astronomer. And I'm convinced, I've been asking people, give counterexamples, and I haven't failed yet. If you think you have a counterexample, tell me in class, or if you think of it this summer or next fall, put it in my box. I'd love to see whether there is one. An example in which one can assess the closeness of a predicted value knowing nothing from background knowledge about the Spielraum. My contention is there ain't any such animal. That you always have in the back of your head some notion of what the range of values could be here, what kind of units we're talking about, light years, angstroms, and so forth. And for that reason, I don't think you can quantify the damn strange, or numerify the damn strange coincidence without reference to the Spielraum. Now, there may be some way of doing it that has some sub-Spielraum, but the way I suggest doing it is this is what the theory tolerates, and we take the ratio of the theory tolerates to the Spielraum, and we call that the relative intolerance. Strike that, relative tolerance. And 1 minus that is the intolerance. The intolerance of a theory. I'm using that strong word because Popperian reasons, see. Good theories are highly dogmatic. They don't allow very much. 1 minus the tolerance over the Spielraum. Don't worry about the... If I've convinced you have to have an idea of the Spielraum, don't worry how you get it. I'll come to that. It's going to be a little fuzzy. So this is the intolerance, or the preciseness, or the detail. As I've said before, working scientists who never heard of Popper and don't give a hoop about philosophy nevertheless invoke a Popperian or Salmonian criterion very frequently when they say things like, that theory is really remarkable, the detail with which it specifies the numerical values that you should throw on. All right, that's the component that's the risk-taking side. Now, how about the hits and misses? Suppose that the deviation D, and we're going to relativize that to the Spielraum. And this part is the relative error, or as I call it, the closeness. And my index of corroboration for a particular experiment or a particular statistic from the clinic file is that C for that individual result is the closeness multiplied by the intolerance. So you give the theory more brownie points for being quite close if it took a big risk, and you allow one of these to counteract the other one anytime you have a product like that. So that means that it was right on the nose, but the nose is very wide, may not get any credit than one that was missed by a sizable amount, but because with extremely exact specifications, we're going to counteract the others. Well, what's the range of such a thing as that? It's always nice if we can, when we use an index in psychology, to fix it so it goes from 0 to 1, like a probability or correlation coefficient. As long as you don't get some crazy idea about the metric. But that's not even true in correlations, is it? I mean, the various substitutes for the Pearson R, like tetrachoric and biserial phi coefficient, they are monotone in terms of the presumed latent R. In some cases, there is no presumed latent R. There are cases where you use the phi coefficient that it would be quite silly to multiply, phi when you have symmetrical marginals and have the underlying situation as normal bivariate surfaces, I think 0.63 of the Pearson R. So if you wanted to know what the R equivalent of a phi was, you would divide by 0.63. But that would be an illegitimate operation in a case in which you have no rationale or nothing in your theory for even assuming that there's any underlying thing here, like, for example, blue and brown eyes or something like that, where you don't think in terms of a dimension as generating four people. So what you can do, that kind of stuff, as the psychometricians tell us, depends upon what your latent theoretical model is. In some situations, it's quite sensible to make a transformation because the phi is a substitute for and a proxy for and an estimate of an underlying Pearson R. When it's not that, plausibly not that, then it's not clear whether you should be making that 63 correction or not. Some people would say you should always make that some kind of a correction for things that have a lid on them, for instance, because you are sort of familiar with the meaning of the metric of the correlation coefficient. And that's not a dumb argument. That's a respectable thing to argue. But as long as we steer clear of having any real delusions, like no Jones, we're just making an index, like the cost of living index, you know. Have you ever worried about that? Boy, the economists worry about that. A guy named Fisher, no relation to R.A., wrote a huge fat book in 1922 called The Making of Index Numbers, in which he had 125 different indexes and investigated their quantitative properties. It's a tough problem, the consumer price index, because of the fact that you have to mix apples and oranges. I mean, the commodity basket has got the apples and oranges and the Kleenex and soda pop and toasters in it, and the distribution of people's disposable income over those things depends upon their SES. The proletariat doesn't spend very much of its income on diamonds of that size, and so what happens is that the economy. The way in which the consumer price index is constituted by the economist can depend upon whether you're right or left in your political and economic views. I mean, some indexes have been criticized by the egalitarian socialists as systematically biased against the poor in that they underestimate the extent to which somebody is harmed by a change due to inflation here, because they have less degrees of freedom to reallocate than Mr. Gottrog's does. He goes without his new Chris Craft for 3 years and spends his money on something else when the index changes. Complicated matters. So for heaven's sake, don't think that I have any delusions about this and the metric that would be the true metric known to God. Well, what's the strong case? If we want to monkey with this to get an index that will operate in the range 0 to 1, the ideal case is the case of a thing that makes a very precise prediction, say predicts a point value, like something that predicts a thing to 2 decimal places when the Spielraum is 100 points, or that is, goes from 0 to 1. And approximately 0. And so this thing is going to be 1. We have to worry that it's not going to be exactly 1. Let's not talk about exact points. Correlations aren't exactly 1 either. If there's no error, then D is equal to 0. Now remember how you can get that. You can get that. Here's the Spielraum, and you can get a D of 0 in this weak theory case like this, or you can get a D of 0 in the very strong case by an observed value that lies within a very, very small interval. In either case, D is 0, so this quantity is 0, so this quantity is 1. So what you have there in the nice case is the case of very strong theory that makes a point prediction or an interval which is a very small portion of the Spielraum and gets it right. And that will give you a CI equal to 1. The worst scenario is harder to settle. I'll tell you what I've settled. I don't remember whether my publication list has got this latest one on it or not, so let me put it down. Theories. The strategy of Lakatosian defense and 2 principles that warrant it. And it is in press in a new journal called Psychological Inquiry. Should appear this year, according to the, I think, in the 2nd issue. I don't believe the 1st issue has appeared yet. Has it? Has somebody seen this? So, and it will be criticized by a batch of 4 to 6 psychologists and philosophers whose names, I've suggested some names, and I don't know who they all will be. The bad case, which I, in the article, have settled in a slightly arbitrary, high-handed way, would be a case in which the theory is so feeble that all it predicts is a direction, the usual null hypothesis problem. Now, there's no guarantee that that will always mean a Spielraum with the cutting line in the middle, but that's what I've done for purposes of index construction. So, in that case, this thing here is going to be 1 minus half the Spielraum, or 1 minus a half. And what will be this? Well, if this is forbidden and you miss, when you miss, you can be anywhere in here. And I'm saying, well, if you can be anywhere here, I'm going to say the expected value is in the middle of that, if it's rectangular, or even if it's bimodal, if it's if it's normal or whatever. I'm just saying the average error is going to be, therefore, 1/4. And so this is going to be 1 minus 1/4 in the bad case. That's the expected value. So you've got the bad case is going to be 3/4 times 1/2. And you're going to miss half the time in this crummy situation. So if you work all of that out, the expected value is 5/10 times 1/2 plus 5/10 times 3/8, which turns out to be 0.44. And in order to standardize that and make it act the way we want, we will define confirmation or corroboration index, this thing here, minus 0.44 divided by the complement of 44. That's just the usual index kind of transformation. You see what you're up to. You're saying, well, if this is the worst case, then CI will be equal to 44, as we just showed, and the numerator will be 0. If it's the nice case, then CI will be equal to 1. And the complement of 1 is 1 minus 44 is 56. And so we put that downstairs. So that in the good case of a theory that makes a very precise point prediction and gets it right, where D is equal to 0, we will be having 1 minus 44, which is 56 over 56, which is equal to 1. But we've got to rig it so that the bad case will give us something around 0, and that's the only point of this transformation. If that strikes you as ugly and unaesthetic, you can stick to the original one. Well, that's for a single experiment. Experiments or statistical entries in the clinical trial, I always have to include that. A batch of experiments, you could compute a mean value, and that would give you an idea of how well the theory was doing in terms of the risks that it was taking and its closeness. Now, the choice of the Spielraum, and you could plot this over time. That is, it has a diachronic feature to somebody like Lakatos, and you would see what the graph of C was over time. Maybe for a while it's going great guns, and then kaboom, it begins to fall apart. And the mean, you can't just take the sum of all those little C's, right? Because that's going to get big, even if each of them is small, just by doing more and more experiments. So you have to get the mean C, standardized C, and that means you have to associate that unavoidably with the number of experiments. I'm bypassing replication problems. I'm just assuming that we decide what experiments are admitted into the corpus and which ones aren't. Well, one of the worst problems with it is setting up the Spielraum. And I discussed that in the paper, and I point out, look, if this is supposed to be an index that would function when we study the history of science, then some of the decisions you will make on that subject should be made by studying its performance. But from the armchair, this is one of the few places where soft psychology may be in slightly better shape than hard psychology or even the physical sciences, because so much of our research data comes to us summarized with pure numbers, namely correlations or correlation surrogates. In clinical and social and personality, I suppose 95% of the research studies don't involve dealing with that is, the summary results come out in terms of a pure number. That is, the dimensional analysis cancels IQ or dollars or years in jail above and below. And the correlation coefficient is a pure number, and so are its various surrogates like C or eta or epsilon squared or tetrachoric or phi and so forth. So in those cases in which the nature of the research that you're doing eventuates normally in a correlation, R or some R surrogate, you have a kind of a natural Spielraum specified, namely a correlation from 0 to 1. Now, in other cases, if somebody's in some area of psychology where typically the research outcome of an experiment doesn't take that form, say I'm studying some aspect of memory and I'm not correlating two kinds of memory, but I'm studying the process, then some kind of conventions would have to be set up. There I adopt a principle from Justice Brandeis that I have quoted to you before. The important thing is often not to have the best rule, but to have a rule. You could, for instance, say, memory experiment consists of range from remembering nothing to remembering everything. Bad. You could say that in some physiological measure, or the effect of a drug on some physiological measure, that you will define the Spielraum as the complete range, namely from the single subject with the highest score to the single subject with the lowest score. You might amend that a little bit by saying, no, I won't count outliers, in which case we have to establish a suitable convention for an outlier, where the outlier is taken to be an error of measurement or somebody from a different population. Those are the two usual cases. You might use the Pearson range, which I recall was go bad. You could say that in some physiological measure, or the effect of a drug on some physiological measure, that you will define the Spielraum as the complete range, namely from the single subject with the highest score to the single subject with the lowest score. You might amend that a little bit by saying, no, I won't count outliers, in which case we have to establish a suitable convention for an outlier, where the outlier is taken to be an error of measurement or somebody from a different population. Those are the two usual cases. You might use the Pearson range, which I recall goes from the 10th to the 90th percentile. That would be another possibility. Is in the paper, I don't want to argue the merits of those various approaches. You can say good things about all of them and dangers about all of them. The main point would be that in a given research domain, a convention would have to be set up for how you choose the Spielraum when the research evidence does not come out to you from your printout as a correlation coefficient or something that is a monotone function of a correlation coefficient, or can be transformed into a correlation coefficient, or is a proxy for a correlation coefficient. Well, I think that's kind of fun. I mean, I think that the philosopher of science who takes seriously his own advice that we got to do empirical studies of the history of science would profit by having something like this. And I contend that a crude way of getting at a damn strange coincidence is more than a more precise way of probabilifying types, the weak use and the strong use. In general, my view, as you expect of any clinician, is that it's better to have a somewhat coarse way to answer an interesting question than an extremely precise way of answering a dumb one. And so for that reason, I'm willing to play fast and loose with things like this and say, well, the empirical evidence will show whether this has any merit or not. Now, a second one that I've been working on, which is less defensible. Maybe this doesn't strike you as being very defensible, but wait, the next one is even less defensible. Well, let me pass these out while I'm at, before I forget. Gives you some examples there so you get a little more concrete feeling about how the thing might work. The second one that I've been working on deals with a different kind of prediction that we don't run across very much in areas like clinical or counseling or social, but that we do run across in learning theory, memory, cognitive psychology, sensation perception. And that's the case where a theory is strong enough to generate a prediction about the functional form that will relate to observables. But it's not strong enough to derive the parameters. It says that y is some function of x, where x and y are both observables without theoretical constructs, where the function f is a plus bx, or is k log x, or is k 1 minus e to the minus ax, or something. But the theory isn't strong enough to tell us what these guys are. And it isn't maybe even strong enough to tell us that the parameters in one experiment can be moved over into another, the way they do in these information processing experiments. It may be strong enough to tell us something about the relations between constants. For instance, you might have a theory that enables you to say that it's linear a plus bx, and there are huge individual differences in people's parameters there. However, it turns out that b is always between 1.8 and 1.9 of a, or something like that. But let's have a theory that's too weak to do any of those fun things. It doesn't tell you the parameters, and it doesn't tell you that whatever the parameters are, fitted now by you rather than predicted, can extrapolate to another related but not identical context, and it doesn't tell you the internal connections between the parameters numerically. But it does say it's a first-degree equation, or it's a growth function, or it's a parabola, or whatever. So I might have some perception or emotion psychologist might have some theoretical variable theta that was arousal, and he might say that theta is, say, a times x, where x is the stimulus intensity. And then he might think that y, which is the latency, is inversely related to arousal. That'd be a couple of plausible things to conjecture. But he doesn't know A, and he doesn't know B, and he doesn't know the relation between A and B. But he does say this is a linear input function to the internal or mediating variable theta, and this is an output function that the theta determines a reaction time, from which, of course, he concludes that xy equals some constant k that the theory doesn't specify. That comes right out of his algebra, and that tells him that the observed data can be fitted by hyperbola, but it doesn't tell him what the constant is. All right? Well, what in that case, you would be fitting your data to various candidate functions, and your theory predicts that it should be a growth function, or a logistic function, or a linear function, or a second-degree polynomial, or a power function. And the question is, do you get it right? So you do a curve-fitting job. It doesn't tell you how to draw the curve. It tells you what kind of a curve to draw, and you have to do a least squares fit or some other kind of fit, if you don't like least squares anymore, to determine the constants. Well, how do we assess the damn strange coincidence of something like that? Beats me. But one kind of interesting possibility is to say, well, I've got a big pot of possible functions, and if I had some way to get roughly the probability of those functions as they pop up in a given domain of nature, say learning in the white rat or perception in the monkey, then I could Now, this will offend some of you, no doubt. I could perhaps use those p-values that I got empirically from the study of the domain and to ask how much of a damn strange coincidence have I got. Now, if you don't believe that meta theory should be conceived of as the empirical theory of scientific theories, then that way of doing it certainly wouldn't appeal to you at all. But if you believe that, then it might appeal to you a little bit. The question is now, what's the Spielraum? The Spielraum is not going to be a number, it's a function. How do we get a Spielraum? How many single-valued functions are there? Does anybody know the answer to that one? That's a real spooky thing. How many single-valued functions are there in mathematics, all told? Well, the first transfinite cardinal aleph null is the number of integers, and the second transfinite cardinal c is the number of points on a line, uncountable set. Well, c to the c, for God's sake, is f, which is the number of single-valued functions. So we aren't going to get any help from the mathematician. You might say, well, we could look up all the functions we got handy in some obvious source, like we take the mathematical supplement to the Handbook of Chemistry and Physics, and we leaf through back there and we look for all those integrals, all those indefinite integrals. Well, depending on what table you're looking at, there might be a punk one would have maybe 100 of them, and a good one would have maybe 400 or 500. That isn't going to do us any good either, right? Some of these are things that arose because of certain problems in physics. Others came to be just because somebody was getting a master's degree in vessel functions or whatever. So that isn't going to do us any good. Well, my crazy idea there, and it's pretty loony, all right, but it should be tried. Should be tried. Proliferation, as Feyerabend says, is to start with an empirical survey of the functions that have popped up in the broad domain that you want to do this for, like human learning, for example. And to take a random sample of textbooks, handbooks, and of the research literature and tally the functions as they pop up and set up some plausible stop rule, like I'll quit when the last 25 articles I've sampled haven't turned up a new one yet, and the last new ones that I have turned up make up less than, say, 1% of all the tokens, not the types, all the tokens. See, that'd be plausible. So what am I doing when I'm doing that? I'm saying I'm going to go out to extremely rare ones, that's all. 0.01, 0.001. If they get to be as rare as 0.01, you probably would not be interested in making a comparison between the damn strange coincidence of a function that had a prior probability of 0.01 and one that had a prior probability of 0.001. At least I wouldn't find that very exciting. Now, if that's a mistake, you can correct that. So my notion there would be that we, in a given scientific domain, we make an empirical study of what kinds of mathematical functions have fitted data, and we make kind of an atlas, and we attach a p-value to each function form depending on that survey. And you know what would happen in psychology. You can get up to 15 or 20, and then you're really going to run out of gas. After that, it's what, 0.01 or 0.001, I don't know. The functions that we're familiar with, and they're not all that different in psychology from chemistry either, or astronomy or genetics. We have linear function. We have a second-degree polynomial, third, fourth. You get past the quartics, you hardly ever run across anything above the fourth degree. If you do, it's because somebody is using Taylor's thing to get to substitute for something that he admits he doesn't know. And they do that more often in physics than we have occasion to do it. Growth functions, decay functions, the logistic function, the Gompertz function, hyperbola, parabola, log, a sigmoid thing of which the integral of the normal curve is only one case, but more broadly anything ogival like that. I suppose we can say gamma and beta, if you, normal curve. You can get up to 15 or 20, and then you start talking about oddball, scarce ones that might not appear in 1 in 200 or 300 articles. So what you would have is your atlas of functions that says functions of form a plus bx occur with probability 23, a plus bx plus cx squared with probability 1. It won't be that big. We're going to run out of total probabilities in a hurry here, you see. And you've got this distribution, and then what you would use for your Spielraum component of that index would be simply the prior improbability of that particular function. Now, what do you use for the closeness? What's the equivalent of the closeness? If I fit a linear equation by least squares, and I show that that fits as well if I do an F or something as some competing thing, is the measure of goodness of fit corresponding to closeness in the other index, where you have a point value or an interval, is the goodness of fit to be measured by the residual sum of squares, which is the way we would naturally think of it. No, unfortunately. And the reason that you wouldn't do that is that the size of the residual around your best fitting curve will depend not only upon whether it's the right curve to fit, but upon the range of individual differences in the particular variant that you're studying, and upon the unreliability of the measuring instrument. And both of those will be big factors in psychology. And that would mean that I might give a theory a black eye just because people differed a lot in their parameters, see? And you don't want to do that, do you? That's not what you're studying. We're not asking whether our theory accounts for all the individual differences. We're saying, given that there are individual differences and given that there are errors of measurement, I want to say how good a job I did over and above that. And I don't know how to do that, but what I suggest in the paper is taken from one of the standard sources in regression theory, or applied, Draper and Smith's applied regression analysis, 1981. That's one of those encyclopedic books that has everything under the sun in it and treated with great rigor. And so it's hard for people like us to read, but you can find an awful lot of good stuff in that. And my notion, they distinguish between, in talking about fitting functions to data, between pure error and lack of fit, which is exactly what we're up to here. They point out that if I fit a hyperbola or a straight line or a log function to some data, that total sum of squares of the individual observations around the best fitting smooth curve has got these two distinct components. That lack of fit means that Omniscient Jones knows that there is some function here that's not quite the straight line that I fitted or the hyperbola that I fitted, that I have not been lucky or clever enough to think of the function which, if I had used it, would fit these data better. Now, you got to be careful about overfitting. You know, there's that trivial thing you learn in college algebra, that for any k points you can always fit a polynomial of degree k minus 1. It'll pass through all the points. But of course, meanwhile, it does all sort of goofy things in between. And if you collect some more empirical data, they won't be on the line. So we don't want to play that kind of games. But you do have, you have fitted something. And the reason that there's a sum of squares of departures from the individual, between the individual observations and the smooth fitted curve, is divisible into these two components. This is individual differences, variance, and measurement error. This is you didn't fit the function that Omniscient Jones knows is the true mathematical function here. You fitted something that's an approximation to it. You fitted a straight line, and you should have fitted something that bends just a itty bit at the ends or something like that. Now, they point out, and I'm not going to go through the algebra of it. In fact, I can't. I don't have anything with me. But they point out that it's not a complicated business. It's just like the general formulas you get in analysis of variance. And it's, well, it's not distribution-free because you're going to do an F-test. But the algebra of it is distribution-free. That is, you break up the total sum of squares about your smooth curve into the deviations of the means of the arrays or intervals from the curve okay, this is the mean of this region, and these are the means. Okay, now this distance here is how far that guy is from the smooth curve, and this is the distance and so forth. And then we have a dispersion of the individual points about those x's, which are the means of the intervals. And those are the two contributors to error. And so pure error is estimated by pooling these dispersions about the mean of an array, and then what's left is lack of fit. Now, if you estimate the dispersion of the means from the curve that would occur if there were no lack of fit, you can estimate that from this, and you can do an F. They're incident significance testing, and you know me, I ain't, oh, I would in this case, I would want to do that, but what I would want to do then is have an index that compares the estimated dispersal of the deviation of the means from the smooth curve and the actual deviation of the means from the smooth curve over the estimated. So I'm saying what proportion, to what extent is this one thing farther from the other than it ought to be. Without doing a significance test, then I will have a crude measure of the relative contribution of these two things. And you can do some fooling around. I don't want to take time to do that either, but you can do some fooling around then to normalize that or standardize that so it will take on values in the region from 0 to 1. Now, there is a problem that arises there, that's analogous to one that arises in the interval index thing. And that is, what if something is a worse fit in some sense than you should get by chance? In the CI thing, I didn't talk about that. We have, in the interval case, we have, let's say, here's the region that's allowed and all of this is forbidden. And what if in one experiment after another I'm not halfway in here, but I'm always farther away, as if nature was against me? Well, I don't know what to do with that. That will generate negative values. And I don't know about negative values, but it's kind of interesting to think about that, because if a theory was consistently doing that much worse than you could do flipping pennies, it's as if it had some deep structure verisimilitude to it, meaning that it's apparently somehow talking about the right stuff, but in the wrong mathematical way. So that's a very interesting thing to reflect on, and it won't get you any trouble if I'm wrong about that. It'll just mean that from time to time you'll get some things less than 0, and you'll say, this dumb theory does worse than I could do flipping pennies. All right? Now, suppose one had, I'm really going to smoke the opium pipe now for a few minutes. Suppose one had some indexes of theory performance like that. Suppose you had 4. One was pointer interval goodness. Another one was predicting function forms. Another one was the embedment in Comte's pyramid. So I can predict some things higher up in the pyramid. Say I can predict some sociology from psychology of learning and motivation, and I can derive some of the psychology from physiology, not all of it. So that's the embedment in Comte's pyramid. Reducibility, another way of referring to that. Two-way reducibility. Something is reducible to my theory, and my theory is reducible to some highly corroborated theories lower in Comte's pyramid. And let's say a fourth thing would be measure of qualitative diversity that the theory speaks of. Very important. Loudon makes a federal case about that, as did Popper early. One of the strongest evidences for a scientific theory is it predicts a bunch of stuff about things that on the surface look to be totally unlike each other. So the Einstein's relativity theory predicts the bending of that ray in the eclipse of 1919 and the perihelion of Mercury, which was already known but puzzled. And then somebody comes along and says, well, electrons, as they go pretty darn fast, and so as electrons go closer to the speed of light, their mass should increase, and consequently the hydrogen spectrum should be somewhat different from the way Bohr said, and a fellow named Sommerfeld worked that out, and that fits. So now we're talking about electrons rather than the sun, and so forth. One of the big things that impressed cultured people about Freud's theory, I'm sure, was the qualitative diversity. The fact that you could look at Shakespeare if you're a literary critic, you could look at anthropology, you could look at nursery rhymes and about the Wicked Witch and Jack and the Beanstalk, you see castrating his father and all that stuff, and it all hangs together in one big ball of wax or can of worms. So diversity, qualitative range is an extremely important thing in corroborating scientific theories. We would much rather have 10 successful doublet replications over 10 areas than have 20 experiments on the same design. Suppose you had 4 measures then. Got the pointer interval accuracy, function form accuracy, embedment in Comte's pyramid, and qualitative diversity of the things that the theory speaks to. And you could go back in the history of science far enough so that you were able to divide theories into things that you're practically certain are substantially correct. They've been in the organic chemistry book now since the year 1930, let's say, and we know about the benzene ring, and it's flat and something else isn't, and so forth. And you could then take these 4 measures over the theories of some domain, some broad domain like chemistry, and you could correlate these 4 measures. Taking the theory, say, at the half-life of its experimental history, that's good enough. We'll just say if a certain theory is now in the books and everybody believes in it, and they've done 147 experiments now, we'll go back to half of 147. Again, adopt a convention. And now we'll divide our theories, and we can then correlate these things, and we'll have a 4 by 2, 4 choose 2 or 6 correlation coefficients, and we could do an old-fashioned Spearman tetrad differences criterion and ask whether one factor suffices to account for this. If you had more than 4, then you'd have to do a factor analysis. Then, and we would get weights then, right, on the loadings on that factor. Now that's a corroboration thing. That's the theory's performance in the short run or the half run. Then, instead of that, we take those same 4 measures, and now instead of studying their ability to predict each other, we will set up a linear discriminant function and assign the lambdas so as to get the best discrimination between the theories that won out in the long run and the theories that were slain. You following me? So there I have an external criterion of sorts. I'm asking which of these 4 halfway in its theory's experimental life was the most powerful predictor and which were weak predictors of whether it's going to be a winner or not. And then, smoking the opium pipe, we would look to see whether the profile of the lambdas resembled closely the profile of the alphas of the factor loadings. And wouldn't that be lovely if they did? Not exactly, but nice, because then we would have had a link between corroboration and verisimilitude, which Lakatos says is a sheer leap of faith. One can think of situations in the history of science in which instead of having theories that survived in their original form, had to be amended by a large amount, and that complicates matters because you're going to have some kind of an index then of the theory in its original pristine form before it got amended consecutively, you know. How close is it to the form that it had that is now enshrined in the textbook of chemistry? So that gets like a pretty complicated business. I don't accept the Lakatos position that the relationship between verisimilitude as an ontological concept and corroboration or confirmation as an epistemological concept is a sheer leap of faith. If you are starting with Hume's problem, it would be. Because if you start with Hume's problem of induction, then believing anything, including that the sun will rise tomorrow, is a sheer leap of faith. But no scientist worries about that. Scientists do worry methodologically. That is, I think I quoted Geary to you before saying Newton worried about methodology and wrote about it and wrote extensive correspondence and put it in the Principia, but he never worried whether if he did the experiment the same way next week it would come out the same way. As he didn't worry about Hume's problem. And the working scientist doesn't need to. I'm not saying you shouldn't if you have philosophical interests, I do. But the working scientist doesn't have to worry about Hume. Well, he does have to worry about the relationship of corroboration and verisimilitude, about how the track record relates to the theory's long-term success. And if you're a realist, that's what you're intrinsically interested in. If you're not a scientific realist but an instrumentalist, you're still interested in that because you want to abandon a theory that's going to be abandoned sooner rather than later, right? So even from the instrumentalist, non-realist point of view, it's desirable to have some way of getting at those. Now, I think I have a proof of why Lakatos is wrong if I'm allowed a little whiff of induction. He says you have to have a whiff of induction, and I say, well, then take a deep breath. The hell with it. If you got to have a whiff, it's already a philosophical sin. So you might as well breathe deeply. And so if I make the assumption that the world is orderly, that there are natural laws, and protons are still going to be protons next month, and so forth, then I think I have a rigorous proof counter Lakatos, which unfortunately we don't have time to go into. But what it amounts to is I start out. This will appear in a working paper of the Philosophy of Science Center, by the way. I don't have the nerve to send this to a journal. But we have our own little internal publishing system, like the law reviews do. You know, you have a captive journal if you're a law student or a law professor. Essentially what I do is start out with O.J.'s theory, Omniscient Jones's theory, the true theory, its postulates. And then I start altering one postulate at a time. So I'm departing from O.J.'s theory. Now, I don't give a damn how rich the experimental literature is. There's a finite number of theorems that I can derive about rats in the Skinner box or people memorizing nonsense syllables. It may be 20,000, but it is not infinite, from a given postulate set. And so we can trace out what happens when we take O.J.'s theory and now we move to theory Ti, where the subscript I means that we've struck out postulate I. We've either literally struck it out of the list or we've altered it in some way. Well, of course, if that's what you do, then all of the experimental consequences in a derivation chain that include postulate I will now screw up, won't they? I mean, if everything else is kept constant and you change that one, if you were making a satisfactory mathematical prediction from O.J.'s theory, which by definition you will, now if we take theory Ti, which alters O.J.'s by striking postulate I, the whole family of experimental designs in which the derivation chain includes postulate I will now be screwed up. You have to worry about the case in which you change one postulate and then change another postulate and undo the blooper that the first one did. I call that a formal undoing, and if we forbid that, which we usually would, if you saw that a scientist had taken away with the right hand what the left hand did, for example, he has y is some linear function of x, and it turns out that he makes theta equal to x to the 1/3, and y equal to theta cubed, you aren't going to hold still for that, are you? You're going to say, what are you doing, Professor Glotz? You got this damn linear thing here, and you're telling me that there's an intervening variable, which is the cube root of your input, and now you've got an output, which is the cube of theta. You've got to give me some additional justification before you can play that kind of silly games. So that's what I mean by a formal undoing. If you don't have formal undoings, and you don't allow some hidden variables, namely things that where I say I've got theta, and I tell you I'm going to conjecture that theta is equal to theta 1 plus theta 2 plus theta 3, but these are not separately connected to any input or any output. You won't let me do that either, will you? You will say, wait a minute, you can't play that kind of game. You have to give me some justification for decomposing theta. Well, it's interesting that if you order theories Ti, Tij, Tijk like that you can show easily, I think you can see intuitively, that if this pair of subscripts always contains this one, and this triplet contains this pair which contains this one, that each alteration in Omniscient Jones's theory screws up more and more of the derivation chains, so that a crude measure of corroboration, namely how many experiments rang the bell, just how many came out, quote, right, without even doing anything like my index, you can order these theories if there are no undoings permitted and show that the rank order of the theories as you degenerate them more and more, moving farther and farther from OJ's literally true theory, will screw up more and more and more of the experiments. If there is a core postulate that appears in every single derivation chain, then not one experiment will come out right, will it? I mean, if T sub I appears in all derivation chains, like in Hull's system, the habit strength thing appears everywhere, at least implicitly. If that one's wrong, then every experiment on the rat that you do will come out wrong, if there are no formal undoings. I also am able to show, that's a clear ordering, isn't it? Ti, Tij, if I asked you for your intuitive notion of verisimilitude, you would certainly say that a theory which contains these three postulates goofed up is in worse shape than one that has only two of them. But what about Ti versus Tjk? Well, now that we're getting into trouble whether we can ordinate them. For example, you might say, well, I'm not sure that that's in worse shape. It's got two altered postulates. But what if Ti is core and Tjk are peripheral? It's not obvious to me about the verisimilitude relationship. Yet if you imagine a big set here, you begin to think, well, if it's got 14 postulates altered versus only one, I am going to say that it's in worse shape unless I is a core one that appears in every single derivation chain. Well, it's not very hard to show by a little set theoretical manipulation that that if the number of derivation chains in which I occurs exceeds the number in which either J or K occur, if that is true, then it can't be the case that Tj exceeds Tik, or that Tk exceeds Tjk. And that's very interesting, because that means that if we fool around with a triplet and one of our corrupted theories changes one member of the triad and the other one changes two, that the worst scenario is in which only one of these three comparisons reverses the ordination of corroboration versus verisimilitude. The other two can't. Now, if you plug that into Spearman-Brown's rank correlation coefficient formula, you can show that you can say with theories that contain 10 basic postulates that the expected value with the worst scenario of the Spearman rank difference between the verisimilitude and the track record will be in the high 80s. And I find that very reassuring. The worst scenario will give you something in the high 80s. So I think I have shown, but I don't Imre Lakatos being no longer among the living, I don't know whether he would concede this. I think I've shown that if you give the scientist or the philosopher of science a whiff of induction, allow him something like the postulate of permanent kinds and the postulate of limited independent variety, as Keynes called it, then it's not true that corroboration is linked to verisimilitude by sheer leap of faith. I have no real objection, being an ex-Lutheran, to leaps of faith, but I don't like to have, I prefer it in church or politics and not in science, and so I don't like the idea that we say, well, the evidence supports this theory, but that doesn't give you any reason at all to think that it's truer than one that isn't supported by the evidence. I think that's a scandal of the jaybirds. So I'm pleased to be able to show fairly rigorously that there is a connection between these two, even with the bad taking the worst scenario, provided you assume that the world is constant in that fundamental sense, that the basic postulates of a domain don't change over time. Well, I told you I was going to talk about the Ines condition, and we can't explain the Ines condition in 3 minutes, so we won't. Okay. If you want to know about the Ines condition, you can find the site in my paper in the Journal of Medicine and Philosophy, the one that says specific etiology and other forms of strong influence. I describe the Ines condition in there, and I give you the reference. Thank you.